are sort of striations, little ridges and troughs created in the regolith by the ejecta, by the exhaust from the lunar module. If you look at the upper right picture, you can see that in that case, the regolith was quite fluffy and the foot pad sank, probably 1 to 2 centimeters into the regolith. On the lower right picture, you can see that, in fact, the foot pad is just sitting on the regolith. So how compact and how fluffy the regolith varies from place to place. But none of it, in no place, is that fluffiness deeper than about 10 centimeters. There's been a lot of discussion about dust and what it does to astronauts and hardware and rovers and spacesuits and things like that. The picture is of Gene Cernan after EVA-3 on Apollo 17. He's just pulled his suit off, and you can see that he's got a lot of dirt on his face, not because the regolith came into the suit during his EVA, but because the suits, which you can see piled on the ascent engine cover in the background, were pretty dirty from walking around on the lunar surface. There's been a lot of discussion about levitated dust. There's been a lot of discussion about whether dust is a critical design issue that will cause failure if it's not followed or not paid attention to. Levitated dust has been suggested both by the horizon glow taken on the surveyor cameras and by photographs and notes made by Gene Cernan as the Apollo 17 command module approached the Terminator. There's been a lot of discussion, is dust levitated? Does it move around on the lunar surface? There's a couple of things we can look at to try and get some idea of whether there is a large-scale transport of dust on the surface. The first is that on Apollo 11, 14, and 15, we put laser retroreflectors on the surface. Now, these were corner cube reflectors that were designed to reflect laser light back to the Earth. So if there's dust moving around, you would really expect those corner cubes to get covered. And even if they're not completely covered, you would expect to see some reduction in the signal strength coming from the moon over time. The Apollo 11 retroreflector has been on the moon now for over 48 years. The others somewhat less time. There has been no evidence of any degradation in laser signal over the lifetime of these arrays. So if there's dust moving around, it's not covering the retroreflectors. When we went to the moon on Apollo 12, we landed near the Surveyor 3, which had spent 31 months on the lunar surface prior to the arrival of the Apollo 12 crew. Although there was some dust coating on parts, the patterns on the coating indicated that the dust was blown onto the Surveyor either by the lunar module landing or by the engines of the Surveyor itself. Again, there was no evidence of dust having settled on the spacecraft from any other source other than the engine exhaust. In fact, there was even a study published where a research team looked at the Surveyor parts brought back to the Earth, and they saw no evidence that dust was on these parts except by blown on by the engine bells. Now, when we establish an outpost, because engine bells do blow dust around, we're going to have to be careful about where we land our spacecraft so that we don't spray dust all over our habitats, deployed equipment, and instruments on the surface. So in that case, we will have to accommodate the fact that if you have an engine coming past the surface, it's going to blow dirt around. There's been some discussion also about whether dust is moving in the Terminator. When the Terminator comes by, there's some suggestion that there are variations in the electrical current, which some people have suggested would cause dust to levitate. So I want to talk a little bit about that particular issue as well. And this concern was raised before Apollo, and Apollo, I think, provides us some pretty conclusive proof that it's not happening. The first, I think, that's really important is that the albedo gradients between the highlands and the mare, the highland rocks being lighter colored, the mare rocks being darker colored, are sharp and distinct. They're preserved at remote sensing scales, they're preserved at photographic scales, and the crews on the surface could see them. In the upper right, the right is a picture of the Apollo 17 site. you can see very clearly that the highland terrains are distinct from the Mare fill in the valley. At the left, you have a geologic map from a publication in 2002 that shows, by using remote sensing data, that those albedo variations indeed represent compositional variations, and that there is no sense that there's a homogenization of the lunar surface from dust. Likewise, if you go up to orbital altitudes and look at things like the Mare highland boundaries, in this case Mare Crisium, on the left you see the albedo picture, on the right you see the iron map, and again you can see clearly that iron does not bleed over into the highland terrain, that the boundaries, the albedo boundaries, are as sharp in the remote sensing data as they are in the visible light. LADEE was a spacecraft I talked a little about earlier as having been sent to the moon recently to look at whether there was a dust component in the high-altitude lunar exosphere. And in fact, LADEE saw, while there was some tenuous dust, there was no evidence of electrostatically lost dust at high altitudes. Lastly, if a lot of dust was moving around, we would expect the rocks at the surface to be either covered in dust or at least have a mantle of dust. And there is no evidence on rocks that have been essentially exposed to the surface for hundreds of millions of years of any accumulated dust blanket. We conclude that lateral dust transport on the moon, if it happens at all, is very inefficient and is not coating the lunar surface with new dust every time the sunrise goes by. Let's talk briefly about the origin of the moon. We'll get into more detail in subsequent lectures, but there were three traditional modes that were advanced prior to Apollo. Some of these modes date back to literally Charles Darwin's grandfather. The first was what we call the fission model. The idea was that early on in the history of the Earth, when it was largely molten, and if it was rotating fast, mass dissimilarities would cause a bulge to be created, and you would essentially birth a moon from that mass distinction. Darwin's grandfather actually suggested that the Pacific Ocean was where that body came from. The second origin theory was that both the Earth and the Moon essentially accreted in the same spot, but created two different bodies, what we call co-accretion. And lastly, we thought that potentially the Moon was formed elsewhere in the solar system and was ultimately captured by the Earth when the Moon in a different orbit came nearby. We know for sure that the moons of Mars, for instance, were captured in such a way that they're actually asteroids which were forced out of the asteroid belt and were captured by Mars and are now permanent satellites. So one of the outcomes of the Apollo program was we discovered that these models are, for the most part, wrong. And we did that on the basis of understanding that the Moon had undergone a fairly violent early history, and by inference the Earth, and also by looking at similarities and differences between lunar samples and terrestrial rocks. After quite a few years, and I mean like a decade, more than a decade after Apollo, that length of time was necessary to really assimilate all the data and start to come up with new models of the formation of the Moon. And what is now called the giant impact hypothesis is the reigning model for the creation of the Moon. What we believe now is that very early in the solar system's history, in some cases no more than 10 to 15 million years after the formation of the solar system, a Mars-sized body impacted the early Earth. And it didn't have a straight-on impact, it had a glancing impact. That the energy of that impact destroyed the impactor, the Mars-sized body, and significantly disrupted the surface of the Earth, such that you created basically a ring around the Earth, created entirely of the impactor plus some of the Earth's crust. Over a relatively short period of time, they think on the order of less than 1 million years, that ring system coalesced to form the moon that we know now, and it has been evolving ever since. It's important to point out that before Apollo, we thought the moon was essentially a big dust ball. Very little in the way of history, very little in the way of internal processes, and at some level, a fairly boring object. But we now know that shortly after the moon was formed, the upper several hundred kilometers of the moon were melted, probably by a combination of impacts and the dynamic environment the moon was in at the time, and it created what has come to be known as the magma ocean. So if you can imagine an ocean, but not of water, of molten rock, you get an idea of what the early history of the moon was like. Shortly after that crust stabilized, we think around 3.9 to 4.2 billion years ago, the last remnants of large planetesimals, big rocks floating around the solar system that hadn't yet been swept into planets, impacted the moon. And these impactors created the big basins that we see now. Shortly after that, we had a massive eruption of basaltic lava. Those rocks are darker and heavier than the lighter anorthosites, and they filled in the large impact basins and largely gave us the picture of the moon that we see today. Since about 2.5 billion years ago, we think the moon has been largely quiescent, not much going on, except for an occasional impact. The smaller the rock hitting it, the more of them there are. Occasionally there are big smacks like Tycho, but that's been the history of the moon ever since the end of the big period of volcanism around 1 to 2.5 billion years ago. And the real key thing about the moon, I think, is that it really has witnessed a lot of the history of the inner solar system and specifically the Earth-Moon system in a way that we can no longer see on the Earth. And consequently, it's not only an important scientific target, but it's a place where we'll learn how to live on planets other than the Earth as we move out into the solar system.
Practicing Artemis moonwalks in the desert, a developmental milestone for our lunar roving robot, and previewing our new polar climate mission. A few of the stories to tell you about this week at NASA. In preparation for Artemis missions on the moon, we conducted a week-long field test near Flagstaff, Arizona. With flight controllers and scientists monitoring activities from Johnson Space Center in Houston, a field team including NASA astronauts Kate Rubins and Andre Douglas practiced moonwalk scenarios, performed technology demonstrations, and conducted hardware checkouts and other Artemis science-related operations. This was the highest fidelity Artemis moonwalk mission simulation the team has performed to date. The team building our Viper lunar rover recently passed a system test readiness review, clearing the team to begin environmental testing of the rover.